Hi, my name is Joseph, and I'm the instructor for this session.
Hi, my name is Kushi. I'm the interviewee.
Okay, so Kushi, can you tell me a little bit about your background with calculus?
Yeah, I took AP Calculus in high school, but I don't really remember much because it's been a while.
Okay,
That's the last experience I've had with math.
okay, so how do you feel about derivatives and like limits?
Um, I really like them. I just don't remember much about how to do them.
Okay, um, so for the first part of this session, how about we refresh on the connections between a limit and a derivative?
Okay.
So can you maybe go into the definition of a derivative? Maybe like using a graph? I just want to see like what you know already about it.
Um, yeah, I can like try and show what that would look like. So
Okay.
here is a graph, and let's
Mm-hmm.
say this is point A and point A plus H.
Uh-huh.
I'll give us a little random graph, right?
Yep.
Okay, we have point A and point A plus H. So I'm not sure about this, but I think from what I remember, this would be a secant line.
Mm-hmm.
And to find, let's say we wanted to find the slope at point A specifically, right?
Okay, yep.
We would have to, obviously, this like graph curves, so you can't just find a slope using 2 points for this graph.
Yep.
Um, you can take this slope, and I believe you can find take the derivative of point A to find its slope.
Yep.
That's what I remember. I'm not really sure how to explain that well, but yeah.
Okay. Well, yeah, that's pretty close. So, um, what if we started converging the 2 points, like A plus H moving towards A? What would happen to the secant line?
Um, eventually it would just become like the tangent line of point A.
Yeah, and what would you say that that would represent as far as like a derivative goes?
Um, like I was gonna say like the slope, but I don't know.
Yeah, that's right. So,
Okay.
uh, can you maybe explain in your own words what that slope would be as far as the tangent line, or like how that would relate to the derivative at point A?
Um, well, like as A plus H converts to A, or like it starts getting closer and closer to A, the
Hmm.
secant line just becomes its tangent line. Um, yeah, I'm not really sure how to explain it, but I know like the tangent line would become like equivalent to the like taking the derivative at point A. It would be the
Yeah,
same
okay.
thing.
Yeah, all right. So that's good. And have you worked with L'Hopital's rule in the past, like when you took AP calculus?
I have not too in depth, but I have seen L'Hopital's role.
Okay, can you share what you know about L'Hopital's or what you might guess it's for?
Um, I don't remember it too well. I just remember that when you're trying to find a limit, if
Hmm.
if you try and plug in that limit into the equation and it comes out as 0 over 0, it would be indeterminate. So you can
Hmm.
use L'Hopital's rule to take the derivative of that equation, and then when you plug it in, it should give you an answer. But if you don't get one, you can keep taking the derivative until you get one. That's
Yeah,
what I remember.
okay. Um, I just want to ask if there was a discontinuity between those 2 points, do you think you could apply the same idea of like the secant line becoming the tangent line and that tangent line being the derivative?
No, from what I remember about like jumps and discontinuity, you can't find derivatives with them.
Okay, yeah. Okay, so now I just want to show a little video to maybe ease our way into L'Hopital's rule.
Okay.
So I'll screen share that right now. Just give me a minute. Screen. I'm sorry, I don't know. Oh, right here. Okay. Can you see that?
Hmm?
Okay, so yeah, this video is just gonna go a little bit into a visualization of L'Hopital's and how it works and why it works. I just wanted to share this.
Okay.
Okay. Can you hear it?
Did you start the video?
Yeah.
Oh, I can't see it playing.
Oh, hold on. Zoom share. Share. Okay, can you see that?
Yeah.
Can you hear it?
Yeah.
Okay.
Can't hear it. But there's captions.
Okay, so you could read the caption?
Yeah.
Okay. Wait, maybe if I take my headphones.
But there's a problematic value
Now I
in
can.
x equals 1. When you plug that in, sine of pi is, well, 0. And the denominator also comes out to 0. So the function is actually not defined at that input, and the graph should really have a hole there. This also happens, by the way, at x equals -1, but let's just focus our attention on a single one of these holes for now. The graph certainly does seem to approach a distinct value at that point, wouldn't you say? So you might ask, how exactly do you find what output this approaches as x approaches 1, since you can't just plug in 1? Well, one way to approximate it would be to plug in a number that's just really close to 1, like 1.00001. Doing that, you'd find that this should be a number around -1.57. But is there a way to know precisely what it is? Some systematic process to take an expression like this one that looks like 0 divided by 0 at some input and ask what is its limit as x approaches that input? After limits so helpfully let us write the definition for derivatives, derivatives can actually come back here and return the favor to help us evaluate limits. Let me show you what I mean. Here's what the graph of sine of pi times x looks like. And here's what the graph of x squared minus 1 looks like. That's kind of a lot to have up on the screen, but just focus on what's happening around x equals 1. The point here is that sine of pi times x and x squared minus 1 are both 0 at that point. They both cross the x-axis. In the same spirit as plugging in a specific value near 1, like 1.00001, let's zoom in on that point and consider what happens just a tiny nudge dx away from it. The value sine of pi times x is bumped down, and the value of that nudge, which was caused by the nudge dx to the input, is what we might call d sine of pi x. And from our knowledge of derivatives, using the chain rule, that should be around cosine of pi times x times pi times dx. Since the starting value was x equals 1, we plug in x equals 1 to that expression. In other words, the amount that this sine of pi times x graph changes is roughly proportional to dx, with a proportionality constant equal to cosine of pi times pi. And cosine of pi, if we think back to our trig knowledge, is exactly -1. So we can write this whole thing as negative pi times dx. Similarly, the value of the x squared minus 1 graph changes by some dx squared minus 1. And taking the derivative, the size of that nudge should be 2x times dx. Again, we were starting at x equals 1, so we plug in x equals 1 to that expression, meaning the size of that output nudge is about 2 times 1 times dx. What this means is that for values of x, which are just a tiny nudge dx away from 1, The ratio, sine of pi x divided by x squared minus 1, is approximately negative pi times dx divided by 2 times dx. The dx's here cancel out, so what's left is negative pi over 2. And importantly, those approximations get more and more accurate for smaller and
Okay. So that was the little clip that I wanted to share.
Mhm.
Let me just stop sharing there. Okay, so what did you think about that video? Did you understand like the visualization? Just
Yeah, I'm still a little rusty on like the pie chart. Like I think I did that even before calc and stuff, so it's not as easy to understand, but it definitely helped me remember the whole purpose of L'Hopital's rule
uh-huh.
and how to use it.
Okay. So did you see how the proportions were preserved?
Yeah.
So that's why L'Hopital's works. It's because the ratio at which the two functions are changing are preserved through the
Right.
derivatives, right? Okay. Um, yeah, okay. So now I just want to ask you a few questions. Do you think L'Hopital's rule can be applied to non-rational functions? So functions that aren't like a top function over a bottom function.
I don't know.
You know? Okay, so based on what you saw in the video, like what might you guess to that question?
I would say um I would say no, but I'm not sure just because anything could be put over one, and if you take the derivative of one, um is it, I'm pretty sure it's one, right? Or is it zero?
Zero. Yeah.
Okay. So and then it can't like you can't really take the derivative of one, or you could, but then can you apply L'Hopital's rule to that?
Um, Not necessarily because we don't have anything to plug into.
Okay. Oh,
Uh,
right, because there's nothing to plug into the bottom, right?
and you can't divide anything by zero, right?
Yeah,
So I
that
wouldn't
makes
say
sense.
that, yeah.
Got it.
Mm. Yeah, so yeah, you're right on that idea that it doesn't really work for non-rational functions. We kind of need those two functions, the ratio between them to sort of apply this rule. Right. Okay. And how do we even know when to apply L'Hopital's rule? Like, in
Um,
what might we actually need it versus when we don't need it? What do you think about that?
I think you can figure out if you need it when you plug in the the limit you're trying to approach. And when you plug it in, if it's indeterminate, then you know you can use that rule to probably try and find the closest value. Or if you see like a hole in a graph or like a jump or any kind of discontinuity, you
Mhm.
can try and apply that method.
Okay, and what do indeterminate forms look like? Do you remember?
Um, in what sense? Like written down or a
Yeah,
graph?
written down, like what's an example of an indeterminate form?
Well, that would be like 0 over 0, right?
Hmm.
So you mean like in an equation?
Yeah, so yeah, over zero is one of them. What about if we were taking a limit to infinity and there were two polynomials on the bottom and top functions? Where would that take us? If
Um, I don't remember.
okay, so do you remember like direct substitution of like taking where we're going to take the limit and just directly plugging it into the equations?
Yeah.
So if we plugged in the infinities to both the top and bottom functions, what would we get?
I don't remember how that one works, but I understand what you're saying, because you can't really plug in infinity.
Mm-hmm.
So there you would have to find another method to,
Yeah.
yeah.
Okay, so yeah, that's right. Now why don't we actually just jump into a few problems so that we can actually apply L'Hopital's rule and see how to work with it.
Okay.
So I'm going to share my screen on my iPad. Wait, I have to share screen. Okay, can you see that?
Mm-hmm.
Okay, so let's try. Limit as, sorry. 5t to the fourth minus t squared plus 1 over 10 minus t minus 9t. And we're going to take this as t approaches 1. Okay, maybe like write it down and then
Okay, so we're taking the limit as t approaches 1 of 5t to the fourth minus 4t squared plus 1 over 10 minus t minus 9t cubed, right?
Yep, I'll stop sharing this so that we can see your screen more.
Okay.
Yeah. Oops.
So if we plug in 1, well, I can wait for you more.
I'm sorry.
Okay.
Oh, wait, wrong. How do I stop sharing? Okay.
Oh, you got it. There you go. Okay.
All right.
So you just plug in 1 and you would get 5 times 1 minus 4 times 1 plus 1 over 10 minus 1 minus 9.
Mhm.
All right. And then that would give you
Make sure you
5.
don't forget your exponents, like on the t's. Right. Like t to the fourth, t squared.
Oh, wait, am I doing something wrong? Because if you plug in 1 here, 1 to the fourth power, wouldn't that just be 1?
Okay, so you just did that already. Like, yeah, okay.
Oh, yeah.
Mhm.
Yeah, I didn't put the exponents up just because I could put those up. I just didn't because it was 1.
Mhm.
Okay. Sorry, don't mind my handwriting. Okay, so that should give you 5 minus 1, 5 minus 4 plus 1. So that would be 2, right?
5 minus 4. Yep.
Okay. And then 10 minus 1. So you have 9 minus 9, which would give you 0. So you can't have something over 0, which is why you would use L'Hopital's rule.
Mhm.
So if we apply L'Hopital's rule to this, we could do the limit as t approaches 1, and then take the derivative of this function. So we can do 20, can you see my handwriting?
Yep.
Okay, 20t to the third minus 8 t, and then that would stop there because the derivative of 1 is 0, and then put that over. I'm going to flip this equation around actually and rewrite it as negative 9t.
You can always do that if that helps.
Yeah, this will definitely help me. Minus t plus 10, which would be the same thing. So I'm going to take the derivative of this, and we're going to get negative 27t squared and minus 1, right? Okay.
And then,
What happened?
so yeah, what would you do now after?
You can try and plug it in now. So if we try and plug in 1, we should get 20 times 1 to the third minus 8 times 1 over negative 27 times 1 squared minus 1.
Yep.
And then we get, can I use a calculator?
Yeah, you can use the calculator.
Okay. Okay, so 20 to the third give us 8,000 minus 8.
Where did you get this 8,000?
I did 20 to the third. Oh, you know what? I don't even know why in the world I did that. Sorry, I forgot the 1 was in there. So it would just be 20 minus 8. Okay. I don't know why I need a calculator then. Okay. So then we would do negative 27 just times 1. So we get negative 27 minus 1, and then we can simplify that and get we get negative 28 down here, and we get 12 up here.
Okay.
So then we can simplify 12 over negative 28. You see that?
Mhm.
And then we can get, we divide that by 2 or 3. No, not 3, just 2, right? Am I missing a number? 4. Okay. So we get 3 over 7, right?
Yep.
Okay. And
Yeah.
then that would be our solution.
Yep, that's our final answer.
Okay.
Okay, so yeah, that looks good. So if you had to put it in words, how might you explain, how might you like connect this answer back to the question?
So you can say that the limit as t approaches 1 would be negative 3 over 7.
Yep.
Okay.
All right, that looks good. Okay, so why don't we try another problem?
Sorry, I don't know what happened to my Wi-Fi.
Sorry, yeah,
Okay.
it's not close it off, but let's get back on track. So yeah, let's try out one more problem. I'm gonna do same thing. I'm just gonna screen share and I'm gonna write down the problem.
Okay. I'll write it with you.
Let's try this one. Limit x to 3 of root x plus
3.
1 minus 2 over x cubed minus 7x minus 6.
X cubed minus 7x minus 6. So we can try and plug 3 in, and then you would get the square root of 3 plus 1 minus 2 over 3 cubed, which should be 27 minus 21 minus 6
Mhm.
And that would get you 3 squared, okay, it would be 2 minus 2 over 0 equals 0 over 0. So we know that's indeterminate form. We can use L'Hopital's rule by taking the derivative of the top and bottom of this function. So we can do limit as x approaches 3. Can you see that? Sorry, I like can't see what I'm doing. And then this is the same thing as rewriting x plus 1 to the 1/2. So we can do 1/2 of x plus 1 to the negative 1/2 minus 2. And then we multiply this entire thing, right?
Mhm.
By for chain rule, and we'd multiply it by x.
So what's the derivative of x plus 1? Because we want to multiply the derivative of the inside function, right?
Yeah. Oh, it was 1.
Yeah, okay.
Yeah. Right.
1
Okay, and then we can put that all over 3x squared minus 7.
Yep.
And then we can simplify that, or we don't even have to, we could just plug in 3, right?
Yep.
So we can do 1/2 times 4 to the negative 1/2 minus 2 over 3 times 9 minus 7. We get 27 minus 7, and we get 4 to the negative 1/2 would that be negative 2 or 1/2?
So 4 to the, wait, can you pan the paper down more?
Oh
Sorry.
yeah, sorry.
So 4 to the negative 1/2.
Is the same thing as 1 over 4 squared.
Yeah.
So it'd be 1 over it would be 1/16.
1 over, or not 4 squared, but
4 times 2.
what is raising a number to a rational exponent? What is that like equivalent to?
Taking the so it would be taking the root of it.
Mhm.
Okay, so it would be 1/2.
Yep.
Okay. So 1/2 times 1/2 would be 1/4 minus 2. And a fourth minus 2 is the same thing as saying we can change this to, instead of writing 2, we can write 4 over 8. Oh no, 8 over 4, I mean. 8 over 4. So we get negative 7 over 4 over 20.
Mm-hmm.
And we can simplify this by, I can't remember how to do this. Hold on. Negative 7 divided by 4 divided by 20 is equivalent to,
So
give it a
what
common
happens?
denominator.
What happens when we divide by a fraction?
You can multiply by its reciprocal.
Yep. So if we had negative 7/4 over 20.
We
Over
can multiply it
20.
by negative 4 over 7. Or no, we would multiply, you have to make a common denominator first, right?
Well, how could you rewrite 20 so that it matches this rational form? What could we put 20 over?
We could do 20 over 1.
Mm-hmm. And then if we're dividing by 20 over 1, what would,
Multiply by 1 over 20.
yeah.
So
So
we could just leave negative 7 over 4 and multiply it by 1 over 20.
let's multiply with the reciprocal and we
Okay.
get,
We get negative 7 over 80.
yep. And
Okay.
see that that's a finite number, so it looks like we're good.
Okay.
All right, so that looks
So
good.
the limit of x, the limit as x approaches 3 would be equal to negative 7 over 80.
Yep.
Got it.
This is L'Hopital's rule, so
Sorry, I'm not sure what the beeping is.
okay. So yeah, that's about all we have today. I just want to ask, what problem did you feel was hardest between the two that we did today?
Um, I think maybe just the second one, just because it like felt like it was getting easier. I think it was just like basic algebra that I was struggling with,
Yeah, it's just
not
like
just being familiar with it.
okay. Um, and why did you feel like the first one was easier?
Um, it was, I mean, it was pretty simple, like deriving.
Mhm.
So I didn't think it was too complicated. Once you derive it once and you have the answer. You just have to plug it in and it gave you a final answer right away.
Mhm.
Same thing goes for this one. I got caught up with the fractions.
Yeah, a lot of people might get intimidated by fractions, but
Yeah.
hi, I'm so sorry. There was a connection issue, but yeah, we're back. Wait, are you muted?
No.
Oh, okay. So yeah, that was all we had for today. Do you think, are you comfortable with L'Hopital's rule? Like, do you think you could maybe even teach it to somebody else?
Yeah, I think like the basic rule I could probably teach someone else. If there were like more complications in it, I might struggle a little bit. I just have to familiarize myself with it. But so far I think it's like pretty easy.
Okay. Um, and yeah, that's all we have for today. So thank you for joining me.
Of course.
Um,
Thank you for having me.
no problem. And yeah, bye-bye.
Bye.